Hello everyone, and welcome back. I am 𝐒𝐲𝐫 a senior CPU design verification engineer, currently working at Synopsys. So I have been working here at Synopsys for more than 1 year, and before this, I have worked in Intel for more than 2 years. Before that, I did my MTech from IIT Kanpur, and studied VLSI there, uh, and got very good grades. Okay, so today we'll be starting in this video. We'll be starting with the HDLBits problem solving. Uh, so under modules we have procedures. So that is what we'll be starting today with. Uh, so whatever we have covered previously, do check them out. And yeah, after that we are starting from the next topic. I'll be sharing my screen. And as always, before seeing these solutions, please do solve it yourself first. Okay, and then like once you have solved it, if you want to look at some other solution, or if you want to basically are stuck and not able to understand how to proceed, then you can just watch this solution. Okay, so welcome back. And today we'll be starting with these procedures. Always block. Since digital circuits are composed of logic gates connected with wires, any circuit can be expressed as some combination of modules and assigned statements. Okay. Since digital circuits are composed of logic gates connected with wires, any circuit can be expressed as some combination of modules and assigned statements. Okay. However, sometimes this is not the most convenient way to describe the circuit. It says any circuit can be expressed as some combination of modules and assigned statements. However, sometimes this is not the most convenient way to describe the circuit. Procedures, of which always block are one example. There are many kinds of procedures. Always block is just one of them. Provide an alternative syntax for describing circuits. This always block provides an alternative syntax for describing circuits. For synthesizing hardware, two types of always blocks are relevant. Okay. For synthesizing hardware, two types of always blocks are relevant. One is combinational always block, and another one is clocked always block. Okay. One is the combinational always block, another one is the clocked always block, which is always at the rate positive edge of clock. So this always block gets triggered when any of the signals present in that circuit toggles. Okay. So it, inside that always block, whatever is present on the right hand side, it takes all of them as, basically trigger points. Like it checks for all those signals. Okay. In case of this, it only takes this clock in the sensitivity list. So whenever there's a uh, rise in the clock, so whenever clock goes from 0 to 1, basically whenever there's a positive edge in the clock, then only this will get triggered. Okay. Combinational always blocks are relevant to assign statements. So combinational always blocks are equivalent to assign statements. Okay, they are equivalent to assign statements. Thus, there is always a way to express a combinational circuit both ways. So we can, you know, uh, either use a always block or an assign statement, and we can express a combinational circuit in both of these ways. The choice between which to use is mainly an issue of which syntax is more convenient. It is like we check whatever seems more convenient, we go with that. The syntax for code inside a procedural block is different from code that is outside. The syntax for code inside a procedural block, the syntax for a code inside a procedural block is different from the code that is outside. Okay. How it is different? So procedural blocks have a richer set of statements. Inside procedural blocks, we can write if then, case statements, and many other things. Okay. But they cannot contain continuous assignments. We cannot say assign. Okay. But also introduces many new non-intuitive ways of making errors. Okay. I mean, there are ways. So if there are many complex things, we can do mistakes. All those are there. Procedural continuous assignments do exist. Procedural continuous assignments will exist, but are somewhat different from continuous assignments and are non-synthesizable. So these kind of procedural continuous assignments are possible, but they are not synthesizable. Okay. So inside always blocks, we can write or assign something statements, but those are not continuous assignments. Those are all, uh, you know, like non-synthesizable things. Okay, those do not get synthesized. For example, the assign and combinational always block describe the same circuit. The assign and the combinational always block describe the same circuit. Both create the same blob of combinational logic. Both will recompute the output whenever any of the inputs or right side things changes value. Okay, right side things means assign out equal to this. This is the right hand side. Okay, both will recompute the output whenever any of the inputs here on the right hand side changes the value. So whenever any of these change the value, out one will change according to that. Here also always at the rate star. So whenever any of these changes, this will be recomputed. This is continuous assignment. Okay. Whenever any of these changes, the value directly reflects here. But here, these are recomputed whenever these any of these four values change. The equivalent value is recomputed and put into out2. Okay. Assign statement. So here we have A, and this A goes to the combinational logic where the output is actually a wire. So this output assign will output a wire. And in case of always block, okay, out2 needs to hold the value when A, B, C, D are not changing. So some value gets computed and put to output 2, and then until and unless A, B, C, D changes again, out2 needs to hold the previous value. So for that, out2 needs to be a register here. Okay, that is what it is saying. It's a register. Okay, assign statement and always at the rate star block. For combinational always blocks, always use a sensitivity list of star. Okay, for combinational always blocks, always use a sensitivity list. Okay, explicitly listing out the signals is error prone. Explicitly listing out the signals is error prone. Means if I say A, B, C, D, let's say I add some logic of E and I forgot to add E here. Then what happens is whenever E changes, okay, this always block is not computed because it's not in the sensitivity list. So what we do is we give a star, so we don't have to manually, write all of them. Combinational always block always use a sensitivity list of star. Explicitly listing out the signals is error prone because if you miss one, then it gets ignored and is ignored for hardware synthesis. If you explicitly specify the sensitivity list and miss a signal, the synthesized hardware will still behave as though star was specified, but the simulation will not and not match the hardware's behavior. Okay. In system Verilog, always use always combinational. Okay. A note on wire versus register. The left hand side of an assigned statement must be a wire type. Okay, of an assigned statement, the left hand side must be a wire type, while the left hand side of a procedural assignment in an always block, this out to must be a variable type, which is reg type. Okay, these types, wire versus reg, have nothing to do with what hardware is synthesized. These have nothing to do with what hardware is synthesized and is just syntax left over from Verilog's use as a hardware simulation language. And is just a syntax left over from Verilog's use as a hardware simulation language. Okay. Okay. So a bit of practice. Let's solve one problem here. Okay. Build an AND gate using both an assign statement and a combinational always block. So we need to build an AND gate using both the assign statement and combinational always block. Since assign statement and combinational always blocks function identically, there is no way to enforce that you are using both methods. Okay. Build an AND gate using both an assign statement and a combinational always block. Since assign statement and combinational always blocks function identically, there is no way to enforce that you are using both methods. But you are here for practice, right? What we have to do is we have to say out assign and out always block. We have to solve it both ways. So what we will do is we will say build an AND gate. Okay. assign out assign equal to A and B. Okay, and always at the rate star begin end out always block. Anything we want to write within any always block or something, we can write within begin end. Okay, out always block equal to A and B. So whenever A or B changes, always at the rate A comma B also we can write. What we will do is out always block equal to A and B. Okay. Yeah, so it's a success. I hope you understood the issue. I mean, we have to write, implement an AND gate, build an AND gate using one is the continuous assignment, another is always block. We did that. Okay. So now let's move on to the next question. We have always block 2. For hardware synthesis, there are no two types of always blocks that are relevant. There are always two types of always blocks that are relevant. Okay. One is always at the start, always at that positive edge of clock. Clocked always block create a blob of combinational logic, just like combinational always block, but it also creates a set of flip-flops or registers at the output of the blob of combinational logic. Instead of outputs of the blob of logic being visible immediately, the outputs are visible only immediately after the next positive edge of clock. Okay. Blocking versus. So what happens here is, I'll explain. Here it's like in this case, okay, whenever A or B changes, output changes. Here, whenever A or B changes, output doesn't change. Output will only change when clock is present. So whenever clock is present, then only A and B are red. So even if A and B are changing, it seems like there is a flip-flop or register, okay, after which the values of A and B is getting to the output. It's like we have A and B, but that output is dependent on the clock. So there's a register, okay, and it depends on the register. So if I want to draw, let's say here, okay, I'll give me a minute. I'll just connect a drawing pad so I can draw better. Give me just 1 minute. I'll show you now what it looks like. Let's say we have A and B. Let's say we have an AND gate, we have A and B. Okay, and we have some intermediate output, but after that we have a flip-flop, D flip-flop like this. Okay, it's a D flip-flop, and we have Q and Q bar. Okay, and here there's a clock. Here there's a clock. So until and unless I give the clock, I don't get this A and B, basically this A and B to the output. Okay, so we say whenever we say that it's create a blob of combinational logic just like the combinational always block, but it also create a set of flip-flop, create this set of flip-flop, this set of flip-flop. Okay, but also creates a set of flip-flop at the output of the blob, at the output of the blob. If I just it also creates a set of flip-flop at the output of the combinational logic. Okay, instead of the outputs of the blob of logic being visible immediately. So instead of this being visible immediately at the output, the outputs are visible only immediately after the next positive edge of clock. So whenever there is a positive edge of clock, let's say this positive edge of clock comes, then only let's say okay, then only this input or this output of this combinational gate will go here. Okay, so then only this output will go here. Okay, I hope you are getting the point. Okay, blocking versus non-blocking assignments. Okay. There are three types of assignments in Verilog. Okay, continuous assignments, assign x equal to y. Okay, uh, hi. Okay, so we are blocking versus non-blocking assignment. Okay, so there are three types of assignments in Verilog: continuous assignments, assign x equal to y. Okay, this can only be used when not inside a procedure. This can only be used when not inside a procedure. That is when it is not inside any always block or something. That is called continuous assignments, which looks like assign x equal to y, like the way we solved questions previously. Then we have procedural blocking assignment. Procedural blocking assignment is uh, like normal blocking assignments, normal assignments that we use inside a procedure. Procedure means like let's say any kind of always block or initial begin end blocks. Okay, that is called a procedure. So when we implement a combinational circuit, we write it like x equal to y. Okay, this can only be used inside a procedure. Procedural non-blocking assignment, x less than equal to y, can only be used inside a procedure. This can only be used inside a procedure. Okay, in a combinational always block, use blocking assignments. In a combinational always block, use blocking assignments. In a clocked always block, use non-blocking assignments. A full understanding of why is not particularly useful for hardware design and requires a good understanding of how Verilog simulators keep track of events. continuous assignments x equal to y can only be used when not in a procedure. This is procedural blocking which can be used inside a procedure, and procedural non-blocking assignment which can only be used inside a procedure. These two can only be used inside a procedure. So this is procedural non-blocking assignment. So whenever one assignment statement is being executed, we can execute multiple, no, the execution actually doesn't wait for this statement to complete. It actually goes on to execute the next assignment. It can be blocking or non-blocking. It continues to go and start executing the next assignments. In a combinational always block, use blocking assignments. In a clocked always block, like in a sequential circuit, use non-blocking assignments. A full understanding of why, a full understanding of why is not particularly useful for hardware design and requires a good understanding of how Verilog simulators keep track of events. A full understanding of why is not particularly used for hardware design. So it's not important if you want to implement a hardware, and requires a good understanding of how Verilog simulators keep track of events. Okay. So you can just know it that okay, for a combinational circuit we will use blocking assignments, and for clocked always blocks, so it's like when we have always at the rate positive or negative edge of clock, we will use non-blocking assignments. And a full understanding of why so is not important. And if you want to learn, it requires a good understanding of how Verilog simulators work, how the events work, and how Verilog simulators keep track of those events and the various areas of those events. We have active region, inactive region, okay, monitored region. So all those regions we will have. Okay. So if you want to just implement circuits, you don't need to understand all of this. You can just use this golden rule, thumb rule, and you are good to go. Okay. Not following this rule results in extremely hard to find errors that are both non-deterministic and differ between simulation and synthesized hardware. So if you don't follow this rule, you will end up in errors that doesn't look like error, and it will be hard to find, and between the synthesized hardware and simulation, there'll be a difference in the behavior. They will result in different behaviors. So it will be more confusing. Okay. So better to follow these rules and avoid all those confusions. So a bit of practice, build an XOR gate 3 ways. Use an assign statement, combinational block, and clocked always blocks. Note that the clocked always blocks produces a different circuit from the other two. There's a flip-flop, so the output is delayed. Okay. What we need to do is, we will say assign, this is the output of assign. Okay. Out assign equal to A XOR B. Okay. Assign this combinational one. Okay. We will not use assign here. Always at the rate star. So it's like whenever anything changes, this value equal to A XOR B. Always at the rate pause edge of clock this output flip-flop equal to A XOR B. So what happens is whenever there's a positive edge of clock, then only this flip flop will get A XOR B. Okay. So I'll submit this. Okay. Uh, let's see what happens. I mean, it will be a success, of course. Let's show you the diagram. Success. Okay. I'll show you the diagram here. So what happens is these are the inputs. Okay. These are the inputs. This is the clock and this is A and this is B. If you see in my, let's say, what is there in the reference output? It's a success. There's no mismatch. But what the reference output shows is it says A and B. If I do XOR, we get 0, 0 is 0. Let's say this one, we'll check 0. And 0 and 1 is 1. 1 and 0 is 1. And 1 and 1 is 0. 0 and 0 is 0. So if you see, this is the signal. And this is getting repeated. Out of assign statement. So out of output of this assign statement. And output of this always combinational, always at the rate star also is the same. If you see out always combinational, this is also the same. You know, it looks the same. Then we have output always flip flop. In this case, what happens is this input happens here after this positive edge of clock, and now because it didn't got the positive edge of clock after it changed, the value changed, it waited for the next positive edge of clock, which is here. After it got the positive edge of clock, it got to know it was 1 and it took that value here. So this value gets delayed by one positive edge of clock, because until and unless there's a positive edge of clock, this input won't be seen and won't be detected and won't be transferred. Okay. So this is the thing. So in case of out always flip flop, okay, this output gets delayed. Okay. So I hope this solution is clear. So let's move on to the next one. Okay, so it says always if. An if statement usually creates a 2-to-1 multiplexer, selecting one input if the condition is true and the other input if the condition is false. Okay. Always at the rate star begin. So it says if statement usually creates a 2:1 multiplexer. Whenever we create a if statement, if this happens, do this. Otherwise, if this happens, do this. Selecting one input if the condition is true and the other input if the condition is false. Okay. So how we write it in the always block? It says always at the rate star if condition, if this is the condition is true, then output equal to x, otherwise output equal to y. Okay. This is equivalent to using a continuous assignment with a conditional operator. We will say assign out equal to condition. If condition is true, x comes to the output, otherwise y comes to the output. Okay. However, the procedural if statement provides a new way to make mistakes. However, the procedural if statement, okay, this procedural if statement provides a new way to make mistakes. The circuit is combinational only if out is always assigned a value. So out should get a value always. Otherwise, out becomes dangling. We get some, latch kind of behavior. Okay. A bit of practice. Build a 2-to-1 mux that chooses between A and B. Okay. Choose B if both select B1 and select B2 are true. Otherwise, choose A. Do the same thing twice. Once using assign statement and once using a procedural statement. So what it says is build a 2 to 1 mux that chooses between A and B, choose B, choose B if both select B1 and select B2 are true. If both are true, then select B. Otherwise, choose A. In all other cases, choose A. Do the same thing twice. Once using assign statement and one using a procedural if statement. If no, all assign we will say out assign equal to if select B1 is true, select B1, okay, and select B2. Why you are saying and is double and signifies bitwise. So this is one input bit, one input bit. If both are true, if both are true, then the output is true. Then we say question mark. Then we give the true result B. When both are true, it says when both are true, output is true. Then it should give B to the out. Otherwise, it should give A. Okay. This is the case. And always at the rate, star. It says, okay, do the same thing twice. Assign statement. Okay. There's no clock needed. And we don't even have a clock. Okay. Always at the rate start. Begin end. What we will do is if this and this, okay, begin end, okay, out always equal to 1, tick B1, else out always will not be equal to, it will be equal to B, and here it will be equal to A. Will not get a value, it will get these values. I mean, it can be multi-bit also. I mean, this is 1 bit anyways because it's written range, but okay. Okay, I think it's good for now. So let's submit. So we can see it's a success. So when this is 0 0 means out equal to A. So it becomes A is copied here. When both of them becomes 1, So here both of them becomes 1. Then this B is getting copied. So from here onwards, we're getting tuck, 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 tuck. So this B is getting copied from here when A and B became 1. Okay, from here. Okay, great. So this is solved. Let's move on to the next one. A common source of errors. Okay, how to avoid making latches. When designing circuits, you must think first in terms of circuits. I want this logic gate. I want a combinational blob of logic that has these inputs and produces these outputs. I want a combinational blob of logic followed by a set of flip-flops. Okay. So this you have to decide first. What exactly you want? How you want the circuit to look like? What you must not do is write the code first and then hope it generates a proper circuit. What you must not do is write the code first and then hope it generates a proper circuit. So we must not hope, we must define the circuit the way we want it to be. Okay. If CPU overhead, o- if CPU overheated, then shut off power equal to 1. If arrived is not present, then keep driving. Okay, is equal to like if not gas empty. I mean, these are not necessarily result in a reasonable circuit. Synthetically, correct code which gives correct syntax, like this can be a syntactically correct code. It does not necessarily result in a reasonable circuit. It sometimes may not be reasonable. Okay, combinational logic plus flip-flops. The actual reason is what happens in the cases other than those you specified. So let's say I specified if this happens, do this. So I said if there is no rain, okay, go to the market and bring some foods. Okay, but if there is rain, what to do? Should should we be hungry, or if there's no rain, we go out and bring some food. If there is rain, what to do? We should cook it ourselves, or we should what we should eat, or what we should do. Okay, so those kind of common questions will arise. Okay, what happens in the case other than those you specified? So it's like book an Uber, and once you get an auto, you know, go, go as soon as possible. What if we don't get an auto for a long time? What is the plan then? There must be some plan B, right? So those things. What happens if this doesn't happen? We should have everything covered. Verilog's answer is keep the outputs unchanged. Okay, we should not change the outputs. We should keep it unchanged. This behavior of keep the outputs unchanged means the current state needs to be remembered. So what Verilog does is, so if I say if there's no rain, go out and bring some food. What Verilog does is if there is rain, it does nothing. It just sees if there's no rain, go and bring some food. If there's rain, it does nothing. It just sits, does nothing. Keep the outputs unchanged. Don't do anything. That's his logic. I mean, that's the obvious logic because you didn't say what to do. This behavior of keep the outputs unchanged means the current state needs to be remembered. You need to remember the current states and thus produces a latch. That actually produces or infers a latch. Combinational logic, example logic gates, okay, cannot remember any state. Combinational logic like logic gates cannot remember any state. Watch out for warning 10240 inferring latches messages. Okay. Unless the latch was intentional, it almost always indicates a bug. So if there is a latch, it's mostly a bug because we didn't load the circuit properly. Okay. It may be intentional in some cases, but it's usually a bug. Okay. Combinational circuits must have a value assigned to all the outputs under all conditions. Under all conditions, we should have everything getting some value or the other. If there's an if, there must be an else, and all of those scenarios must be covered. There should not be any scenario left unattended. This usually means you always need else clauses or a default value assigned to the output. That means we need the else statements or some default value should be assigned previously to the output or later at some later point of time. Okay, not late. Basically, mostly we do some we assign some value previously and then based on the if conditions we assign new values. Okay. Otherwise, we retain those old values. Demonstration. The following code contains incorrect behavior that creates a latch. Fix the bugs so that you will shut off the computer only if it is really overheated. Okay. And stop driving if you are arrived at your destination. Okay. Or you will need to refuel. So what happens here is if not arrived, keep driving. Okay. When it haven't arrived, it keeps driving. Means keep driving equal to 1. Okay. If arrived, then what to do? You didn't say. So it keeps driving because it doesn't stop. So and also it says keep driving equal to if gas is not empty yet, keep driving. If gas is empty, I mean it's okay, it can't keep driving because keep driving equal to not of gas tank empty. So if tank is empty, you know, if tank is empty, this becomes 1. Then not of this becomes 0. Keep driving becomes 0. So it's like if gas tank becomes empty, keep driving becomes 0. So anyways, but till the time there is gas in the tank and we have arrived in the destination, then also it says keep driving because it doesn't change the behavior. Okay. So we need to give an else. If reach destination, stop. So it says, okay, CPU overheated. If CPU overheated, okay, shut off the computer equal to 1. Otherwise, shut off computer equal to shut off computer. Otherwise, this value gets repeated. Okay, the same value gets repeated. So what we need to do here is if CPU overheated, shut off computer. Otherwise, it should keep the previous value. Keep the previous value of 0. Okay. fix the bug. So we'll shut off computer only if it's really overheated and stop driving if it. Okay. Shut off computer equal to 1. So what happens here is it says if CPU overheated, then shut down computer equal to 1. Okay. Else we should not shut off computer equal to 0. I mean equal to 1. Okay. Shut off computer equal to the previous shut off computer. Always at the rate star begin. If arrived, then if not arrived, keep driving till the time gas doesn't become empty. If arrive, else if not arrived means here, else means it arrived, then keep driving equal to 0. So why I did this actually to say if arrived equal to 1, keep driving equal to 0. Okay. That is what I did. If CPU overheated, then CPU shut off computer. Otherwise, shut off computer was 0. So we keep that. Shut off computer is rage. You can say this is 0. And right. Let's see what happens. Okay. Incorrect. Let's see where is the issue. There's a mismatch between my output, which says shut off computer is 0. This keep driving is correct. The shut off computer doesn't work. Okay. Shut off computer should work like this. Shut off computer, CPU overheated. Okay. It becomes 1, but then it should do equal to 0. That means, okay, if I just check now, and now it is success. Okay. Okay, great. What we should have done is shut off computer equal to negative of CPU overheated. We should have done that. Okay. Anyways, there are multiple ways to do it. We shouldn't have done shut off computer. I thought if it shuts off, it should not switch on, but it's a different kind of problem. I hope you understood. What should we have done is we should say we don't need this if else. Whenever overheat, shut off computer should be 1. I mean, if CPU overheat is 1, shut off computer should be 1. So it's like shut off computer equal to CPU overheated. When overheat goes to 0, shut off computer goes to 0. Okay. And here, whenever arrived is 1, okay, if arrived is 1, keep driving becomes 0. So keep driving equal to not of arrived. And whenever gas tank empty becomes 1, keep driving becomes 0. Okay. So it's like not of arrived and not of gas tank empty. If I just do AND of these two, if arrived becomes 1 or gas tank empty becomes 1, keep driving becomes 0. Okay. Otherwise, it remains 1. Keep driving equal to not of gas tank empty. Okay. If tank empty becomes 1, it should be 0. So and not of arrived. It should not have been arrived yet. I mean, the destination shouldn't have been reached yet. So what we can do is keep driving equal to. I just remove this if and else to show you something. Okay. Keep driving equal to. So if haven't arrived, if arrived becomes 1, then not a 1 is 0. So keep driving becomes 0. And if gas is empty, this becomes 1, not a 1 is 0. This becomes 0. Okay. And I can say shut off computer equal to 1 if CPU overheat is 1. This is 1. If this is 0, this is 0. So shut off computer equal to CPU overheated. Okay. So this is not needed. This is not needed. This is good enough. If I just uh, submit this, uh, anyways. So if I just submit this circuit, it will recompile. Okay. And let's see what happens. I hope you will like this solution. Yeah, success. So next time again, second time. Because we removed defills, we just gave the absolute logic. Okay. Anyways. Okay. So uh, let's go to the next problem. It says always case. How we need to write a case statement. That is what have been shown here. Okay. So case statements in Verilog are nearly equivalent to a sentence of if, else if, else if, else if, else. So multiple else ifs in between. That compares one expression to a list of others. One expression is compared to multiple other expressions. There's a list of expressions and one expression is compared with that. Its syntax and functionality differs from the switch statement in C. its syntax and functionality differs from the switch statement in C. Okay. So I know it's a long video, 1+ hour video. Please bear with me. We will cover the questions properly. You can, let's say take a break, pause the video, take a break and come back and then restart. Okay, not an issue. So otherwise, okay, let it be. We will solve the next question here. Okay. So always case statement are nearly equivalent to if else that compares one expression with multiple others. Its syntax and functionality differs from switch statement in C. So what happens is always at the rate star begin. Okay. Case input. Okay. And then if I see what is the value of the input, if it is 1, then begin out equal to 1 tick B1. If there's more than one statement, we need to use begin end. There's no other way. For one statement, we may use begin end, we may not use begin end, like this. Okay. But if there is more than one statement, we must and should use begin end. There's no other way. Okay. So if the value of in is equal to 1 tick B1, then out equal to 1 tick B1. Otherwise, if in equal to 1 tick B0, then out equal to 1 tick B0. Otherwise, default out equal to 1 tick Bx. Okay. So this is the logic we implemented. The case statement begins with case and each case item ends with a semicolon. Each case item ends with a semicolon. Okay. And also default. There is no switch. There is no switch word. Okay. Only case statements. Each case item can execute exactly one statement. Each case item can execute exactly one statement or one procedural block, basically. This makes the break, okay, used in C unnecessary. This makes the break used in C unnecessary. So we don't need to use a break. It is one statement only. So we can write begin end and multiple statements within it, but it is considered one procedural statement. So break is not necessary. This means if you need more than one statement, you must use begin to end. Okay, we need to write all the statements within begin end so that you know like otherwise we cannot, because it is one statement or one procedural block. Begin to end is a block. Okay, one procedure. So inside that we can write any number of statements. Duplicate and partially overlapping case items are permitted. So if there are duplicate case items, okay, so let's say some of this overlap with this. Okay, that is permitted. The first one that matches is used. C does not allow duplicate case items. Here duplication is okay. If there's one set, let's say one set and another set, let's say uh, 1 0 and 1 1. Okay, let's say 0 0 0 1 1 0 1 1. So I can say if the first bit starts with a 1, and I can say if the last bit ends with a 1 or ends with a 0. I mean, there's no mutual, you know, exclusion. Okay, it's not mutually exclusive. It's like I have values 0, 0, 0, 1, 1, 0, and 1, 1. Okay, I can say if the first number starts with a 0, or let's say I can say if the first number starts with a 1, okay, and if the last number ends with a 1. So see, if you see, there's an overlap. If you see, there's an overlap here, and this statement is not covered. So this will go in default. This will go in the default case. Okay, this will go in the default case, and there can be a overlap. So let's say this is first case statement or first condition, condition 1, and this is condition 2. There can be an overlap. Okay, there can be an overlap between these two. So there's overlap here, clearly overlap. Okay, so that is okay. Got it, right? There can be an overlap, and that is okay, perfectly fine. Okay, so it says this overlap is fine and permitted. Duplicate and partially overlapping case statements are permitted. The first one that matches is used. C does not allow duplicate case items. C does not allow duplicate case items. Okay. What happens here is if any of the case statements get executed, let's say one tick B1 gets executed, it doesn't even check the next of the statements. It just goes out of the end case. I mean, just it goes out of the case to end case, block. Okay. And that doesn't happen in C. That's why we need a break statement. Okay. A bit of practice. Case statements are more convenient than if statements if there are large number of cases. So if there are large number of options we need to check. Okay. And if the same variable is being checked multiple times with multiple other variables or values, in this case, the case statement is much more effective and simple to use than the if else statement. Because if else statement, if else statement becomes complicated. Okay. So in this exercise, create a 6 to 1 multiplexer. When select is between 0 to 5, choose the corresponding data input. Otherwise, output 0. Okay. So what we need to do is, and the data inputs and outputs are all 4 bits wide. 4 bits wide. Okay. Case select. ठीक है. 1 tick B 0 0 0. Okay. What we are doing here is we're saying 1 tick B 0 0 0. Here case in. Okay. And then I'll not write begin end. I'll say output equal to this. Okay. Case select. Okay. One colon. Okay. And I'll say, and we don't need a, okay, we need semicolon here, which is usual. We don't need any other thing. We will say out equal to and it says when the select is between 0 to 5, okay, use the corresponding data input. 0, okay, and in case, and we need to write, okay, we need to write a default. Okay, okay, it come here. Okay, good. Right there. Okay, if the select is from 0 to 5, 6 to 1, where select is between 0 to 5, choose the corresponding data input, otherwise output 0. Okay, otherwise output 0. Default out equal to 4 tick b 0000 or 4 tick b 0. Okay, so output becomes 0. Yeah, that's it. Case and end case. That's the logic. Let's submit. Did I give 3 tick? Correct. Oh shit. Very bad mistake. 3 tick b. Success. Okay. It was confused. Like suddenly why 1 tick b. Okay. I hope this is clear. So moving on to the next problem. Always case 2. Priority encoder is a combinational circuit that given an input bit vector outputs the position of the first bit in the vector. For example, 8-bit priority encoder, then the given this would this because is high. Build a 4-bit priority encoder. It says priority encoder is a combinational circuit that when given an input bit vector outputs the position of the first one bit in the vector. For example, 8-bit priority encoder given the input this would output 3 tick D4. Because fourth bit 4 is first bit which is high. From the right hand side it is checking. Okay. For this problem none of the inputs are high. Input is 0, output 0. Note that a 4-bit number has 16 possible combinations. To tick P00 input equal to 0. So we can write all 16 possible combinations. Okay, so input means 4 tick B 0001 something 0000. So I'll say 0001. Okay. In that case, position equal to 0. Else, if this value is 1 question mark means anything. Okay. Position equal to 1. Right, case X. I can say then if this is position equal to 2. Else position equal to 3. Else default is position equal to 4 tick Bx. Position equal to 2 tick Bx. B 00 01 10 11. X. Okay. For this we need to write an n case as well. Write always begin at. Yeah, submit. The incorrect. Okay. Always at the rate star. Okay, if none of the bits are high, output 0. We did opposite. Where we should put X here. Then sub. Now it will be correct. Yeah, success. Great. Actually, it is seeing from the right hand side. While doing, I don't know how I implemented it opposite way. It sees from the right hand side. Okay. So whatever is the first one, based on that, it's set bit 4. Okay. It doesn't see from the left because otherwise this have been bit 7. Okay. I hope this is clear. You can look at the solution. Okay. Yeah. So let's proceed ahead. Build a priority encoder with 8 inputs. I know this video is becoming a bit long. I'll extend for 20-30 minutes more. Okay. Build a priority encoder for 8 input bits, 8-bit inputs. Given an 8-bit vector, the output should report the first least significant bit in the vector, that is 1. Report 0 if the input vector has no bits that are high. For example, the input this should put this. Okay, this should output 4. That is high on the previous exercise. That would be a 256 cases in the case statement. We can reduce this down to 9 cases if the case item in the case statement supported don't care bits. This is what case Z is for. It treats bits that have the value Z as don't care in the comparison. And that is what we did last time. So it's the same thing we'll be doing. It says now do it for this 8 3-bit position. So we'll do the same thing. Case position, sorry, case input, and we will say if the input is 8 tick p xxxx1, then do position equal to 3 tick p000. Okay. That means 1 1 1 1 ऐसे आएगा. ठीक है. And then 0 0 0 0 0 1 0 1 0 0 1 1 100 101 110 111. Default position equal to 3 tick B 000. Okay, and it says we implemented KSX. Okay, that's why we use this. We can use KZ also, but it's not needed. It's the same thing. The case statement behaves as though each item is checked sequentially. In reality, a big combinational logic function. Notice how there are certain inputs like 1111 which will match more than one case item. So 1111 will match this, so output becomes 0. The first match is chosen, out becomes 0, but not any other of the later inputs, any of the later inputs. There is also a similar case X that treats both X and Z as don't care. I don't see much purpose to using it over case Z. The digit question mark is a synonym for Z. So 2 tick B Z0 is the same as 2 tick B question mark 0. It may be less error prone to explicitly specify the priority behavior rather than rely on the ordering of the case items. So it becomes less prone to errors if we explicitly define the priority behavior. So which one should be checked first? For example, the following will still behave the same way if some of the case items were reordered, because any bit pattern can match at most one case item. Okay, in this case, it will match exactly one case item. So if there's a one in any number of ones here and then one here, anyways, I think this is bad mistake actually, because now if this is given here, then this result, whatever the result for this, that will be the output. So we should not reorder. We should put it in a very specific order. Okay, and I think by default it should be 0. Uh, let's okay. We need end case, otherwise we'll mistake. Okay, so we have solved this issue. It's a success. Great. So okay, you can look at this solution. Okay, you can look at this solution, and if you have any doubt, please let us know. Please let me know. I hope you understood the issue, understood the problem, because last one also was related to this. And then we have another question. It says avoiding no latches, always no latches. Okay, avoiding latches. Okay, suppose you are building a circuit to process scan codes from PS2 keyboard for a game. Okay, given the last 2 bytes of scan codes received, you need to indicate whether one of the arrow keys on the keyboard has been pressed. This involves a fairly simple mapping which can be implemented as a case statement. Okay, which can be implemented as a case statement, or if else if with 4 cases. What we are doing is, based on the last 2 bytes, we need to indicate whether one of the arrow key is pressed based on the last 2 bytes. Okay, so this is 1 byte hexadecimal, 8 bits, 8 bits. So last 2 bytes. Okay, which have been pressed. This involves a fairly simple mapping which can be implemented as a case statement or if else if with 4 cases. Scan code 15 down to 0 arrow key. This arrow key is the variable. Scan code 15 down to 0. This is the code and this is the arrow key, left arrow, right arrow, up arrow. Anything else means none. Don't have to do anything. Your circuit has one 16-bit input. There's one 16-bit input and 4 outputs. There are 4 outputs. Okay. Build the circuit that recognizes these 4 scan codes and asserts the correct output. Recognizes the 4 scan codes and asserts the correct output. To avoid creating latches, all outputs must be assigned a value in all possible conditions. Okay. Simply having a default case is not enough. Okay, you must have values for all possible combinations. You must assign a value to all 4 inputs in all 4 cases and the default case. This can involve a lot of unnecessary typing. One easy way around is to assign a default value to the outputs before the case statement. I don't know why. I mean, you can just say default and then give values to them. Okay, 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 okay. Got it. If something is detected, like let's say this is detected, 𝐒072, then I say down arrow equal to 1. Down arrow equal to 1, then what are the values of up arrow, left arrow, and right arrow? We have to give them some values, right? So if I say default, it won't go to default because down it matched this case. So then up, left, and right won't have any value. So previously give some value and change only the ones that are needed. For 𝐒072, only change down arrow value to 1. And default all are zeros. I mean, it's okay. We don't need a default then. Okay. This style of code ensures the outputs are assigned a value of 0 in all possible cases unless the case statement overrides the assignment. This also means that a default case item becomes unnecessary. Default case item is not necessary then. Reminder, the logic synthesizer generates a combinational circuit, okay, that behaves equivalently to what the code describes. Hardware does not execute the lines of code in sequence. Okay, so it doesn't execute the code. The logic synthesizer generates a combinational circuit that behaves like the description of the code. Okay, whatever the code describes, that is what is synthesized to create a logic combinational circuit. That is why it is called, you know, hardware description language. So it describes a hardware. So that's why it's called a hardware description language. Okay. So it's written, okay. Case. What we need to put in the case statement, and we need to do always at the rate star begin end case end, and we will say up equal to 0, down equal to 0, left equal to 0, right equal to 0. So it's like we are putting everything in one sentence, one line, which should be put in multiple lines. Okay. So this is the scan code, case scan code. So that is given as input. Okay. And if we have these values, okay, okay. So whatever is needed, we are making it 1. Otherwise, we are not doing anything, because by default, these all are 0. So I don't have to put a default case here. Okay. By default, it's 0. Okay. So yeah, let's submit this. It's a success. Great. I hope you understood this solution. If you want, you can take a snap or something. But okay. Okay. So this is solved. We'll be moving on to the more Verilog features. The procedures is done. Okay. So we will stop it here. We will cover the more Verilog features in some later video. Okay. Because it's a new topic. We will start in some new video. Okay. So that's all for today in this video. Okay. So if you have solved any problem in a different way, or if you have a better approach, a more optimized approach, please do leave that information in the comments below. Please do drop that in the comments, and I would love to see your approach And if you have any doubts, don't forget to ask me, you know, in the comments. Either me or any of the other people will reply. Of course, I'll be there to reply. And if the doubt is a simple one, I'll reply in the comments. I'll explain in the comments. And if it takes a long time, to explain or something, I'll create a video of it and post the link of that video in the comments. Okay. So yeah, and keep practicing. I'll see you in the next video with more Verilog features. Okay. Like whatever follows this conditional and ternary operators and everything. Okay. And don't forget to like, share, and subscribe this channel. Like and share this video. Okay. Subscribe this channel and let your friends know about it. Share it with your friends so that everyone can, learn from this and, practice it and do better in their VLSI career. Okay. Thank you. Bye.